has a problem with that, but we are going to record it. So if anybody, there you go. If anybody has to jump off for any reason, you can watch it at a later time. So I'll be sharing it with all of you later. So getting into that, today's focus is getting to know all of you. So I am going to make everybody come off of their bubbles and show their faces so that we can just do a very quick virtual around the room if we can. So I just want you to just introduce your name and the university you're from and your major. And if you are a sponsoring organization, you know what to do. So I'm going to start with, is it Ong? Did I say it correctly?
Yes, ma'am. Yes, my name is Ong. Yes. My name is Ong Ponjor. You can call me Ong. I'm a PhD student in electrical engineering and I'm from Auburn University. Nice to meet you all today. Thank you.
Thank you. Nice to meet you. And Rachel.
Hi, I am an undergraduate at Auburn University, and I'm studying biosystems engineering.
Perfect. Yeah. Thank you for being here. Nice to meet you.
Yeah, you're welcome.
Let's see. Next bubble is Lucas DeLong.
Hi, everyone. My name is Lucas DeLong. I'm with sponsoring organization Kleinschmidt Associates. I've been with them working in hydro for nearly 16 years, and I'm an electrical engineer.
Wonderful. Thank you, Lucas. And we're going to hear from Lucas here in a little bit. He's going to give us our little Hydro 101 session in about an hour. So just to give you a little insight. Well, Stacy, since you're there, I'll have you introduce yourself. Oh, you're on mute.
Thank you. I don't use my camera often. Yeah, I am Stacy Graham. I work with Alabama Power in the Reservoir Management Department. We do kind of the day-to-day managing of the dams in our system and the technical studies that kind of the background work that goes behind it. And I've been there about 20 years.
Perfect. Well, we're glad to have you. Thank you, Stacy. And Matt, or do you go by Matthew?
I go by Matthew. My name is Matthew Kozlowski, sorry. I'm an undergraduate at Georgia Tech, and I'm a mechanical engineering student.
Perfect. Thank you. And Kyle.
Hey everyone, my name is Kyle Weiss. I am a PhD student at the University of Tennessee here in Knoxville. I'm studying energy science and engineering, specifically focusing on hydropower and how operational restrictions impact both grid stability and the environment.
All right, awesome. Kyle, thanks for joining. And Eugene.
Hi, my name is Eugene Thompson. I'm a senior undergraduate student at Tuskegee University, and I'm studying mechanical engineering.
Perfect. We're glad to have you. Thanks for joining. Nice to meet you.
Nice to meet you.
And let's see, Ahmed.
Hello, my name is Ahmed Lotfi, and I'm an undergraduate in Sneed College in Alabama, and I'm studying computer science.
Perfect. Nice to meet you, Ahmed. Thanks for joining.
Nice to meet you too.
Matthew Eddy.
Hi, everyone. My name is Matthew Eddy. I'm a graduating senior at Tuskegee University, and I'm studying mechanical engineering. Nice to meet you guys.
Nice to meet you. Thanks for being here. And Tarek.
Tariq Lotfi. Nice to meet you guys.
Tariq, sorry.
That's right. Yeah, I'm studying at Auburn University, electrical engineering. I'm also working at Honda Motors Manufacturing of Alabama. We're building engines. I'm super excited about the renewable energy. That's why I joined this. Thank you.
Awesome. We're glad to have you. Thank you.
Thank you.
And let's go over to Steve Winke.
So we'll give this a try. So can you hear me?
We can hear you all the way from Hawaii. Now you're on mute though. Steve, you're on mute. We can't hear you now.
Try that one. Is that better?
There you go. That's better.
Okay. So yeah, I'm trying to keep things down. I've got people sleeping behind me somewhere here. But yeah, so anyway, Steve Winke. I retired from a utility about a year and a half ago. Up in the Pacific Northwest, state of Washington. Currently president of the Hydropower Foundation, and have been working with Bree and others for a number of years on these projects and these different get-togethers. So I'm really happy to be here, happy to have all of you with us, and look forward to the meeting and getting this going.
Thanks, Steve. And thanks for joining so early in the morning from Hawaii on your vacation. We appreciate it. And I don't know if we heard from Naveed.
Hello, everyone. I'm Naveed. I'm a PhD student at Georgia Tech, and I'm studying material science and engineering. Nice to meet you all.
Very nice to meet you. Thanks for being here.
Thank you.
Okay. And I think Russ is the last one, if I'm not mistaken.
Did you do Steve Lehman also?
I have, oh, no, I haven't done Steven, so we'll get.
Yeah, sorry. Hey, everyone, Russ Sanford. I'm with Kleinschmidt Associates. We're a consulting firm. You're going to hear from Luke in a little bit. I'm a civil environmental engineer by education. And today I work as our chief growth officer, so it's more about strategy and where the market is headed. We do a ton of work with Southern Company, Alabama, and Georgia Power. Our firm is about 85% of what we do throughout North America is related to hydropower. So this is just something that we're really passionate about and glad to participate in. We have offices in Alabama and South Carolina and people all over the Southeast that kind of serve power utilities working in hydropower throughout the area. So nice to meet you all and look forward to seeing you in a few weeks up in Alabama.
Thanks, Russ. And Stephen.
Yeah, hi, I'm Steve Lehman. I'm also with Kleinschmidt. I'm an aquatic ecologist by background, ichthyologist, and I'm in Metro Atlanta. I have graduate degrees from the University of Tennessee and the University of Alabama. And I've been working in hydropower for over 30 years, and I work with engineers on a daily basis. So it's great to be part of this, and I'm so excited to be here. Thanks.
Okay. I think that's everybody. Please raise your hand if I missed anybody. I thought I got everybody. Just happy to have everybody here. I wanted to kind of run through, so I will talk a little bit about teams, and I will talk a little bit about, I'll introduce Steve. He's going to talk a little bit about the challenge at hand. You have not received the actual packet, the challenge. We're still kind of finalizing just a few details. So we're hoping to get that over to you probably about early next week. So, and then following Steve talking about the challenge, we're going to give you the little Hydro 101 session. Some of you, this might be review, some of it might be new for you, but we're going to give it to you as if this is your first time hearing it. So just to make sure that everybody gets the same educational session today. So, and I just want to give you a little rundown. I'm sure that you all noticed there's a variety of different backgrounds that have been selected for this competition, and that's intentional. So what we are going to do, and what I will let you know here in just a few minutes, is your team assignments. But essentially, we break you up so that, you know, we're not going to have all of the PhD students in one team, and we're not going to, you know, we're trying to keep it fair, but ultimately, in the real world, you work with people of all different backgrounds and all different educational levels. So we want to make that experience that you're going to have here at the think tank, we want to make it as real life, you know, as we can. So, so we have split that up accordingly. And there will be 3 teams with 3 students in each team. So you'll have to write this down, and I'll also send you all of the contact information after this meeting, okay? So team 1 is Kyle Weiss, Ahmed Lofty, and Matthew Eddy, okay? And then team 2 is Rachel Shore. Did I say it right? I don't know. Sorry if I butchered that. Right. Okay, Shore. Ong Fan Ka, I'm trying. And then Eugene Thompson. So that's team 2, Rachel, Ong, and Eugene. And then team 3 is Tarek Mustafa Lotfi, Naveed Esfahani, and Matthew Kozlowski. Y'all can like totally throw stones at me later if I butchered anybody's name. So I'm excited to have been able to give you guys your assignment, your team assignments. So I will send you the contact information, like I said, after the meeting, along with a recording of this session so that you have it. And we'll hopefully be able to send you the write-up of the challenge early next week, like I said. So without further ado, I'm going to let Steve Winky take over and talk to you about the challenge at hand. Thanks, guys.
Okay, are you still with me?
We are.
Okay, good. I'm having some technical challenges. I'm sorry with my connections here, but I think we're getting those worked through. So first things, and Brianna, can you pull up the draft of the package we have? I think it'd be useful.
Yes,
for us here.
1 second. I had it pulled up and then it went away, so 1 second. Okay. All right, can you see it? Somebody has to answer.
Yes. Yes.
Yes. Okay, then you're good to go.
Okay, I need to pull up something else. Well, sorry. Really did take some time to get ready for this. I'm just getting there. So.
It's okay. It's early.
Yeah. Right. So click that. Okay. Now we're all seeing the same thing, so I'm finally there. Sorry about that. Okay, so anyway, again, welcome everybody, and I hope you find this problem interesting for yourselves. And you know, there's as we move through this, you'll discover there's elements of this, you know, for everybody on this call. And so we'll kind of go through some of that. But basically, the problem that we're going to be asking you to take care of for us is there's a plant that Bartlett's Ferry, a hydro plant that has, as I recall, and Steve, you can correct me, but I believe it's coming up for relicensing. And so we're exploring some different ways that might be used away from the conventional side. And so one of the things that we came up with, and if you could just scroll down to the picture that says the generation and demand there. So not quite that far. There we go. So basically, what we're asking, and you can see the 30 megawatts of solar highlighted there. But conceptually, there is a system demand that is reflected by that gray curve that you see there. and then there's the output of a plant. And you can see that those two don't really match up real well. And so what we're looking to do is to add a solar field to the project. Of conceptually now, we're not actually doing this. This is your part of the study to try to ascertain how this might work. But if there was a 30 megawatt solar field attached to this project, how can we reshape that orange curve, the plant output, so that it better matches that gray curve? So in other words, use solar to help provide some energy, and then use the hydro plant to kind of match up what's left, so that if the orange curve comes down and matches up with that gray curve more closely. And this happens on a macro scale in places. And scroll down just a little bit further. Could that next curve there? That's good enough. So this is actually a clip out of the California Independent System Operators website. It's kind of interesting, but basically you can see the effects. The turquoise line, if you will, the higher line of the two, is the actual system load, and the stuff that's in the blue color, or the purple color that's below that, is the generation mix of assets that come on. And then that gap in the middle is really the effect of the solar panels of all of California, and how effectively during the middle parts of the day in California, they help meet the energy demand. And you can see how they can turn down the conventional plants. So those conventional plants are, hydro plants. They might be gas turbines, could be contracts that they're buying. There's lots of ways that you supply power to a system, but you can see that gap that's created because of the solar that comes in. And then the real challenge that happens in California, and again, one of the challenges that might show up here, we don't know how this is going to look exactly for your output, your plant, but there's a sharp rate of rise. You can see the box there that is required because the sun goes down relatively fast and people come home in the evening, the loads go up relatively fast. And so there's a high ramp rate. And then, of course, once the sun is down, you can see there's still a number of hours in the evening that you're going to have to cover with your plant as you run it. So that's the essence of what we're trying to do. I can get into a little bit more of it here in a minute, but just real quick, are there any questions about the basics of what we're asking you to do? So I'll just summarize again. Put in a 30 megawatt solar field attached to the plant in some fashion. There's different ways that can be done, but with the effects of solar, so you're going to need to know the output of the sun, if you will, and how that load shape looks, and basically then modulate the hydro plant to match that. And at the same time, and hopefully we'll get into this in this session, but meet all of the license conditions and operating conditions that you have to have with that plant. There's reservoir levels that need to be maintained. There's maybe flow regimes that have to be maintained. There's a lot of different constraints that fit that you have to work within. So you're going to have to come as close as you can to the system here. So any quick questions on the fundamentals of that real fast? It's all clear? Okay.
Yeah, it's clear, but I only have one question. Could we have like more details about like the plants, like the type of plants, the flow ratio, different other different like parameters? Do we have anything like for mathematical basis? I mean,
certainly, yes. So scroll down and get a little bit further, Bree, and get down to the pictures and some of the other descriptions and stuff.
Thank you.
Yeah, keep scrolling. So, oops, there you can see the units a little far. Yeah, that's good. There's the descriptions of the units, how long the reservoir is, the storage in the reservoir, and so forth. And so, yes, we do have more here. And I think also that's some of the details that Bree was referring to that we need to probably get check in on a few more things. But yes, there are more details. It's not that vague. I just kind of wanted to stop at just the basics of the problem we're going to ask you to solve, because once this is done, then we got to fit all the constraints, including the licensing / environmental constraints that this project has, because you're going to change the operation of the project. And so one of the things that we'll ask for is some assessment of what that might mean to some of those environmental considerations. Go ahead and scroll down a little bit further, Bree, to the picture, the map. There we go. So you can see where Bartlett's Ferry is in context of the river system, and there's several other projects around it. But we're only asking you to really look at Bartlett's Ferry. If you had 2 months to do this, we'd probably look at a riverine system entirely and look at all of the effects of changing the operation like that. But we're not doing that, just this project. Any more questions? That was a good question. Thank you.
Just one question. Can you go back and summarize it one more time? I got the part where you're talking about attaching the solar field to the plant, and I got the licensing part, but between that, I kind of lost me.
Okay, yeah. So basically, the basics of the problem that we're trying to do is using solar, and these two pictures were my attempt to try to capture the challenge. There is, you can see the current plant. I think this is the current plant, so this may be a representative plant, but you can see load demand and plant output, how they do not match up. Okay, and so we need to change that orange curve by the addition of solar so that it matches that gray curve. And I think that's also some of the details too, is you're going to get the curves specifically for that area and that plant. I think these are generic curves that are shown, but again, it's illustrative of the problem that the output of the plant doesn't necessarily match up with the load demand. And it's the same thing with the solar too, right? The output of the solar, doesn't necessarily match the demand. It does during the middle parts of the day, and that's kind of what you see below. When the solar comes on, yeah, it can be used to match, but something has to go away. And then when the solar goes away, something has to come up to match it up again. And so it's a gymnastics game that's played between, controlling type of assets that, typically gas turbines and hydro plants usually take that big regulation because they're the most flexible of the assets, hydro being the most, and natural gas fired turbines being also a very flexible asset, often take up the brunt of those kinds of resource mixes. But you can also throttle down fossil units to make all this happen. Again, we're not looking for a big system-wide issue here, so we're just looking at the plant. So the two assets that you have are a solar field of 30 megawatts that isn't there. You're going to have to figure out what it looks like, what the output would be on a given day. So you're going to have to learn a little bit about how solar works and the intensity of the sun and the incidence and so forth. You can make choices on the solar if it's going to have a pivoting system, so it kind of matches the rotation as the earth moves relative to the sun during the day. You can adjust the solar panels or you can keep them fixed. There's different things like that. One of the things I think would be of interest here is there is a floating solar system that floats on the reservoir that might be really interesting, and given the developments around that might be around the plant and so forth, that might be a way to get the solar there. So locating the solar, you'll be amazed how many acres a 30 megawatt solar field is going to take as well. And so it's not a small system. And so that's a part of the challenge, is where you're going to put this and how you're going to get it there. It's 30 megawatts, which is, again, it's not a big one by utility scales and so forth, but it's going to, like I said, that's one of the things you will need to kind of learn as you go, is how much of a footprint that takes. And then where that goes, and how that fits in, and how the sun then, and where the energy goes, and what you need to do with the dam. For example, there may be enough output that you can shut down a unit or two during the daytime of your operation and save that water for later in the day when you need it. So I hope that's a little better description of what we're asking for. Did I address your question okay?
Yes, you did.
Okay. So now, Bree, scroll down a little bit further, and it's got some specific tasks in here. There we go, right there. The task to be considered. So one of the things that, and I'm not sure what Kenneth has in mind to do this, we've talked about having a hydraulic model prepared for you that basically a very simplified model that would allow you to model the reservoir fluctuations as you put flow through the plants. And so again, just conceptually, right? You've got a reservoir, which is a big tank, and you've got water coming into it, and you've got a control valve on the drain side of that tank that you can open and close, which is the hydro units. And so one of the things you'll need to understand is that as I drain more water out, if I'm draining it out faster than it's coming in, that tank is going to start to empty. And again, the license conditions that we talk about is you can only empty that tank so far, then you have to stop. Otherwise, you start violating licenses, and you could get them significant fines from FERC, and people who live on the reservoir don't like it when their docks get dry, those kinds of things. So there's lots of bad things that happen if you exceed those operating limits. And by the same token, if I have it shut down and I got a lot of water coming into that tank, soon the tank will start filling up, it'll overfill and overflow. And again, that, in the real world, that would be like overtopping the dam, which is also something you do not want to do. And so there's a range of flows and stuff that you'll need to kind of understand. And so there'll be a model that needs to be created. This can be done in a pretty simple way. We were just talking for those that are maybe can conceptualize what this might look like, but a simple rectangular volume that, you can determine what comes in, goes out, and you might just solve this on an hourly basis and stuff. So for some of you, that what I just said may make some sense, and for some of you that is foreign language I just spoke. But again, I think this can be done and done fairly quickly and pretty simply, but it is an important piece to understand how your solution with adding that solar, how it's going to affect that flow and what that means. So one of the pieces that you may want to consider is if that has some significant impacts on the operation of the plant, or the hydro plant, maybe there's some modest changes to the license that might be proposed as part of this. Again, that's all in line with what this project is trying to identify. I mentioned the second bullet item there, I talked about the footprint and trying to locate it near the dam, because again, a 30 megawatt field is quite large by some measures. It's not huge, but it does take up space. And so you'll need to kind of work on that. Grid integration, 30 megawatts is pretty significant load. And so looking at the system the electrical grid system that you have there in that area, where would you put those 30 megawatts so that you can safely put it on and utilize that to serve the load? Some of the things you'll have to look at, and again, some of you will recognize some of these things, some of you will not, but like there's transformers that will be required, to step up the voltage from whatever the solar field produces up to a transmission level. And so there's, some space within a switchyard or a new substation or something that would have to get considered for that. Connecting the devices to the power system and the cost to do that. Any changes in the hydro plant control systems that is necessary to implement this. Ideally, it would be nice if you could, conceptualize how the controls might be changed and automated so that this works in a normal way. So there's not a lot of personnel type of innovation required to make this work. And then environmental impacts, recreation, fisheries, so forth. And then also, it's kind of, if time permits, we're kind of looking, look at the solar field and maybe expand it or basically optimize that a little bit to look at, ways that we can be, you can maybe stretch that operation a little bit. So those are the basic topics. So anyway, something popped up. Is that mine? Yes, it is. Nope. Okay. So anyhow,
sorry, I had to charge my phone, so it it popped up a message for me. Sorry about that.
Okay, no problem. So and as those are some of the basic ones that we kind of identified. And honestly, as you start working on this challenge, you'll probably come up with some other things that, well, gee, why can't we just do this? And it's like, perfect. That's what we're asking you to try to assess. And so don't consider this a firm list that you have to check off. These are just some things to be considered, and you need to look at that as considerations. Some of these you may not have much concern about, or be able to do much about. Your teams, as Bree described, we try to put these teams together. Oh. You still with me?
We are now. You went away for a minute. You there?
Said we try to put these teams together.
We might have to regroup with Steve in a minute if he is having technical issues. I think sometimes we take
Bree.
advantage of our, yeah.
Yeah, I might just jump in while we're waiting on Steve. So Steve will be there, and Kenneth Odom, who could not join us today, but Kenneth is also from Southern Company. So there will be some technical folks that are there to be able to make sure the teams have the proper information to be able to come up with their solution for it. But this is not intended to be it's not like a report grade. It's more of coming up with some free flowing thoughts from different teams to how would we solve this challenge. So that's what the challenge is about, and the output will be your presentation and how your team comes up with it, not expecting that that any of the solutions may not be the ultimate solution that goes forward, but it's a good way to help Southern Company in thinking about this challenge as they're looking over their entire fleet of, I can't remember, Steve might know how many hydropower plants they have in Georgia and Alabama. But so that's kind of the context behind it.
Thank you, Russ. Sorry about all that. Obviously my connection got dropped. But yes, I was trying to get to exactly that point when I was trying to emphasize things to be considered. You guys each will all have your opportunities to kind of put your own viewpoint on how this problem and how it might be resolved. And so this is about you coming up with what you think might be a really unique solution, or maybe not even unique, but just what the best solution is to this issue, to try to reshape this, and in the process learn about how this integration between different kind of assets all works together.
That's right. And just to add to that a little bit, the few days that we're in Alabama together, we're going to be giving you all sessions that pertain to this challenge that will help you ultimately. And there's more than just the technical side that is going to be judged. You're going to work in teams. You have to highlight each other's skills. Everybody's going to bring a different skill set. You're going to learn, public speaking and be able to present in front of a group under a certain amount of time. So there's some different things, components that are going into all of this. So just want to ease your minds a little bit that we are going to give you some more education behind this. We're going to give you a Solar 101 when we're together at the think tank, things like that to help you all with the challenge. We're also going to be giving you time to work together in your teams. So just a little background. Go ahead, Steve.
Yeah, no, that's great. If you want to scroll down toward the bottom, there's one last piece of data that I wanted to highlight. Again, it's just information that may or may not be, that one right there, hold up, may or may not be of value to you, but just know that it's there. But it is actually what the value of the energy power that you produce at certain times of the day is worth. And so you can see that shifting output around, and you can, by putting more in the middle part of the day, there's value to be created by doing that. And so again, it's just another piece of information. It's not something, that might be of value to you as you kind of, if you start looking at solutions and understand how the value of the timing of those solutions works, that can also be help you make some decisions or recommendations of what you would do here. And I think at the very bottom is a little bit of the deliverables that Bree was just kind of referring to.
I've been hanging back here waiting to ask that question, right? As a consultant, we get the background of the project here, and talk about all the data that is available or will be made available. And that's the question that's been lingering for me is, all right, what do we need to produce at the end of this? This is good.
And Steve, I think you've been working closely with Ken on the problem. I'm not sure if he was going to add any more detail to this. So that's why we haven't sent it out to you all yet. We wanted to share it today, give you some ideas of what we're going to be asking for, but then also once it's completely, final, then we'll send it out to you all so you'll have a copy of this.
Yeah, Kenneth and I haven't had a lot of exchange on this in the last while, so I don't know if he's got some other information to be added. I think there's a couple pieces that we may want to look at, but effectively, this what what you've been exposed to now is really the extent of the problem that you'll be asked to evaluate and see what your recommendations are.
Okay, great. Thank you for confirming that. Does anybody have any questions about anything at this point, like the competition itself, the problem, logistics?
I had a quick question about the time we're supposed to show up, if that's okay.
Yeah. So that Monday, and I'll be sending you out an agenda as well, which will help you with your scheduling for the week. But students can start arriving between 4 and 7 on Monday evening, and I'll get you the hotel information and everything as well, so you'll know where to go. We're staying at the Courtyard Marriott in Phoenix City, but I'll send all of that to you and get your reservations to you as well. So.
Okay, perfect. Thank you.
Of course. Anything else? Any other questions?
I will offer just one last comment, and this is really in line with what Russ was also saying just a little bit ago, but I don't know if there's a right or a wrong answer to these things, so don't get caught in that. But as Russ was indicating, you're going to be judged on a lot of different elements, on your solution, how well you work as a team, the presentation that you come up with, those types of things. And so just, it's important that everybody work together and respect, each other's knowledge base, and let those, different perspectives come forward as you start trying to circle in on what you think might be a good solution to how this might work. It's just, and you'll get some, I think, Bree, we probably have something on the team, working as teams and stuff as part of the curriculum here. But anyway, it's just important that you understand there's not a hard, fast technical solution we're looking for here. We're really trying to, give you an opportunity to see what the hydro world is like and how flexible that asset class can be and how important it is, and trying to, meet an energy future and learn about what all the equipment is, see it firsthand, and talk to the people who work on it.
I would just add on to that really quick, Steve, that this is meant to be fun and educational, and don't get stressed out over winning a contest. In other words, just come and learn and use your brain power to figure out, some ideas that may work for this.
quick question.
And yeah, go ahead.
Quick question. Just the megawatts capacities you gave, those are nameplate capacities, correct?
I believe so, yes.
Thank you.
Steve, you might know that. You're a little more familiar with the specifics.
Yeah, I believe that's true, and I'd be happy to describe a little bit more about the setting of the project if you'd like, if that would be of interest from the map.
That'd be good.
I think that'd be great.
Yeah, the project was relicensed back in the early 2000s, so it's not coming up for relicensing anytime soon. But if there were to be a major change in its operation proposed, then Georgia Power would have to apply for a license amendment. Okay, so this is the Chattahoochee River Basin, and it originates upstream of Atlanta with Lake Lanier, which is a large water supply reservoir for Metro Atlanta. And the system includes I think it's about 5 Corps of Engineers dams, so very large dams that are operated by the Mobile District of the Corps of Engineers. The Bartlett's Ferry Dam is one of several Georgia Power dams on the river upstream of Columbus. So upstream of Bartlett's Ferry, there are a couple small dams, Langdale and Riverview dams, and Georgia Power is actually going through a process to decommission and remove those dams from the Chattahoochee River right now because they're no longer serving a useful purpose. They're so small. And you can see West Point Dam is the dam upstream near LaGrange, Georgia, and that controls the flow into Bartlett's Ferry. So that's one of the constraints on what water is available at Bartlett's Ferry Dam to generate is how they operate West Point Dam upstream. As you proceed downstream, the next several dams below Bartlett's Ferry between there and Columbus are small Georgia Power dams. There are 3 of them. Well, they're not so small. They generate a good deal of power, but they're in a fairly short segment. And then when you get down to Columbus, there were 2 dams removed since this map was created, City Mills Dam and Eagle Phoenix Dam. That's going to be right where we're staying in Phoenix City. Those were removed, and now there's a whitewater venue there. So there are rafters and kayakers that use that section of the river, and the water that they need comes from the hydro projects upstream. So that's a consideration, environmental consideration, broadly speaking. So after the river flows through Columbus, it then flows down south towards Florida and goes through a couple more Corps of Engineers dams. And then it becomes the Apalachicola River after it combines with the Flint River at the Florida border. And then that goes into the Gulf of Mexico. So that's just a broad overview. There's been a lot of controversy around this watershed over the past several decades because the states share them. 3 states share the water in that basin. And I mentioned drinking water supply in Atlanta, there's power generation. And then in Florida, there's been concerns about the oyster industry having enough freshwater flow coming down the river. And there are also several federally endangered species of fish and mussels at the dam on the Florida line below that dam. So there's a lot going on in this river basin, and it'll be interesting, and I think you'll have fun seeing this project. And if you've got any questions, I'd be happy to answer them now or later during the competition.
Yeah, does anybody have any questions for Steve? Either Steve?
Yeah, I got a question about the very first slide. Yeah, when you see the relation between the demand and the plant output, what you guys do when the plant output is more than the demand? What do you do about this power? Do you have like some kind of you tie electrically with some companies that you actually give them this power, or is it being wasted, or what?
Yeah, so this is a bigger question. So this, what we're trying to do is just match that gray curve to the plant output. And so this is, if you can look, there's, different scales on this, but so in the real world, this singular plant would be nowhere close to that gray curve, just to be clear on that, right? This is a plant of a few hundred megawatts trying to meet a system demand of several thousands of megawatts. And so in the real world, this plant would never exceed that. But in the real world, there are times where you have more resource perhaps than what demand is. And what happens, and scroll down a little bit, Bree, to that next chart, because that's really what you need to do, is you have to back off something. So this is a case where I've got more resource available than demand on my system. And so what they do here is they back down conventional resources. They start shutting down hydro units, perhaps, shut down gas units. And maybe if they've got a lot of wind blowing, they may curtail wind or even curtail solar if they have control of that, to match that up. And then as what in fact really happens is, and it's hard to see, but there's a lot of squiggle in that line. It looks kind of regular line like here, but there's a lot of fluctuation in that line, and so there's a constant balance is also going on. So you got hourly balances and moment by moment balances and everything. So in the real world, and I hope I'm answering your question. So what would happen is, to make that orange curve work, we'd shut units down to bring it back down to that demand. I mean, just look, you're just having created this curve is just as an illustration as much as anything. It seems like just the eyeball average, I could reduce that orange on the front end and fill it back up on the back end, and you could match it up pretty closely to that gray curve, right? I mean, just using your eyeball as an averager there, you can kind of see where I could probably reduce it in the morning hours and increase the output in the evening hours, and then overall have about the same amount of energy out of the plant, but match much better that demand curve. Does that make sense?
Yes, it does. I'm just considering the concept of optimization to go along with the solar array that we're gonna install. You see what I'm saying? So we try to get things to help together. That's why I'm asking this question.
Oh, it's a great question.
I think it might help to picture the gray curve in this context as maybe a local demand or a regional demand. Think about the microgrid concept, right? If you've got a little grid that's islanded from everyone else, you've got a couple of towns and this hydro plant and a solar plant. Kind of isolate the problem with that kind of mentality.
That's a very good point. Any other questions? Okay, hearing none, and that doesn't mean you can't ask questions as we continue on, but I do want to allow Lucas some time to give us a little Hydro 101, and that I think will also help answer some of the questions that might be floating around in your head as well. So Lucas, if you are ready, I will stop sharing and you can share your screen if you have slides or.
Sure. So, welcome again. I'm Lucas DeLong, an electrical engineer with Kleinschmidt Associates. Been doing hydro work since I joined Kleinschmidt in 2007. Happy to be sharing a little of what I've learned with you folks today. So here's the agenda of the presentation. This whole presentation is kind of about the basics. We're going to scratch the surface of most of the hydro topics that would be considered engineering topics, if you will. So we'll go over the basics, how hydro works at the middle school science level, And we'll look at the different kinds of projects, different kinds of hydro projects, different turbine types. We'll talk about generators for a little bit, and we'll talk about controls and protection and automation. So again, back to, middle school earth science, right? Hydro is renewable because the hydrologic cycle is what drives the system. So we have water evaporating and transpiring from lakes and rivers and the ocean, and then being transported via sometimes atmospheric rivers. That's been making the news a lot, to places where precipitation brings it back down to earth, and then transported terrestrially in our rivers and groundwater, so that we can make use of it. It's free fuel. All we got to do is capture it. So here's a nice dense photo of a typical hydropower plant cross section. So this equation gives us a relation for the power output from a hydro plant. So P is power, and excuse me, eta is an efficiency number. Let's say for a typical hydroturbine generator, that's 0.9, 90%. Rho is the density of water. That doesn't change much. Q is the volumetric flow rate. So this is the amount of flow, cubic meters per second, that we can put through the turbine. G is the acceleration due to gravity. That doesn't change much. And H is the height difference between the inlet and the outlet. And so inlet and outlet might be a little bit deceiving there. So we're talking about the height difference between the upper reservoir and the lower reservoir, or the head pond and the tail race. So that is known as gross head or hydraulic head. So power is proportional to flow and head, to put it very simply. So let's talk a little bit about dams. Now, again, I'm an electrical engineer, but hey, it's just dirt and concrete, right? So we've got four main types of dams. We've got buttressed dams, of which I do not have a photo, but picture, the Notre Dame Cathedral with its flying buttresses, right? You've got a big straight wall, and you've got buttresses holding it up. We have an arched dam, like the Hoover Dam, pictured left, and earthen dams. Again, just dump truck after dump truck load of clay and gravel piled up to hold the water back. And gravity dams, I guess, is not necessarily parallel to that list, but think of a gravity dam as a mass of concrete that simply works by gravity not allowing the water to tip it over. So it's not anchored like an arched dam, and it's not buttressed like a buttressed dam. It's just stays in place because it's heavy. So dams are going to have spillways because the water has to flow over them or through them. Usually the through is through the powerhouse, right? But we need capacity to spill water that we can't put through the powerhouse. Usually that's because, the powerhouse isn't designed to take the river's complete flow all of the time. It wouldn't be economical to build a powerhouse that could do that. So the extra water, when there is extra water, needs to be spilled over the dam or through the dam. So we've got several types of spillways that are common. You could divide them into two groups, either a controlled spillway or an uncontrolled spillway. So a controlled spillway has gates like bottom left here. These are tainter gates specifically, or radial gates. They're quite common. Someone will have to, an operator will open the gate to allow water to pass. In the case of a tainter gate, it passes under the gate. Sometimes it'll pass over a gate. So, requires operator intervention or automation. In an uncontrolled spillway, the water simply flows over the crest of the dam, such as both of these photos at the right. So the photo at the top is what's called an OG shape. It's got this hydraulically pleasing curve at the top and the bottom that helps optimize flow and I think dissipate energy. You'll notice at the top of both of these dams, there's pins. In the top photo, the pins have nothing on them. They're just standing there in the way of the water. And in the bottom photo, you can see that there's some breaks where more water is flowing through what's called flashboards. So these are simple flashboards. There's a pipe sticking up out of the crest of the dam and some plywood or some planks across those pins. And this is a very simple type of gate in that when the water gets high enough to a designed level, those pins will fail to allow that high level of water to flow over the dam and not cause flooding. So spillways prevent flooding. Right? And then we have emergency spillways. Oroville might come to mind. The emergency spillway is rarely used. It might be gated or an overflow spillway, but its purpose is usually to relieve, extreme flooding. So an emergency spillway might not be designed with, all of the robust civil attention that a normal service spillway might be. It might be just a low spot in the top of the dam that might be armored with riprap, and then the water would just flow down the dam with some risk of erosion. As well, Oroville was a nice chute spillway, but still. Its emergency spillway was not. And so, again, purpose is to pass excess water. These spillway gates, when gated, can also be used to, control level, obviously, because we don't want the pond coming up so high as to go over the dam at unintended points, but also for flow control. So, again, if you can't control the flow with your hydro station, whether it's because you're on the low end of the capacity or beyond the capacity of the station, you may be able to control it with spillway gates. Let's talk about water conveyance. It's kind of a fancy phrase, but it is what it sounds like. It's a means to get water from one place to another. Usually when we're talking about water conveyance, we're talking about how we get water from the head pond or the upper reservoir to the hydro station. So two good examples are pictured here. On the left photo, we have what's called a penstock, a really big pipe, taking water from an upper reservoir, probably through these series of pipes. And you'll notice that in between these sections of pipes, there are these massive concrete blocks. Those are to hold the pipe in place, obviously, under the force that the water would exert on it as that water makes its way around directional changes in the penstock. This looks like a particularly tricky and steep one. We can also get water from A to B via canal. That's a very old school way to do it. And this photo on the right is of Hadley Falls in Massachusetts. This is a very old mill complex where you'd have several mills along the canal that are all each doing their thing, taking a little bit of water off and returning it to the river downstream. There's Tunnels also, often you'll see tunnels and penstocks combined, especially if you have a very high head site or a site where the upper reservoir is just far away from the hydro plant. Tunnels could be, just tunneled through rock, or they could be lined with concrete. Obviously a costly and complicated endeavor. So the intake structure I would consider as part of the water conveyance. So the intake structure is just going to be the civil works that house the gates to allow water into your penstock or your canal. And then we have, gates and valves along the way, obviously. So at the bottom of these penstocks, there's probably going to be some isolation valves ahead of the turbine. And there's going to be, gates at wherever, hydro plants or a mill may have taken water off of this canal, for instance. Some people might consider a spillway water conveyance as well. Kind of depends on how you think of it, but a spillway moves water from one place to another. Let's talk about project types. This is a fun graphic. Let's start at the tail of this fish. You can divide hydro projects into these three kind of groups. So we've got a run-of-river project, and we'll talk about each of these three in upcoming slides here. A storage project where you can store some energy and cycle the plant. Whereas a run-of-river project is kind of what it sounds like. You take the water as you get it and you put it through your plant. A pump storage project is, again, not quite parallel to these two, but a different type of project where you're able to move water from the lower reservoir to the upper and vice versa, taking advantage of low costs when demand is low and producing power when demand is high. So we can further divide hydro projects into three categories with regard to the hydraulic head at the project. We talk about projects as either high, medium, or low head. And there's different equipment considerations that come with that, particularly the turbine type. We'll talk about those in future slides. Then we have its purpose. Obviously, we think of energy first, or at least I do, but many dams were put there first, not for energy, but for irrigation or navigation, as in a lock and dam, or for flood control, and then energy came later as a side benefit. You'll often find with lock and dams, especially, that energy is a secondary, if not tertiary consideration. It's not at the top of the list for someone who's operating a lock and dam. So a run-of-river facility is allowed, and this gets back to the discussion of constraints. So your category of facility is one of your constraints that is usually tied to your license, right? So a run-of-river facility will, in its license, have very little range of operation for the head pond. And that head pond is your storage. The amount that you can raise or lower your head pond is the amount of storage that you have. So on what we refer to as a run-of-river facility, flow in equals flow out for the most part. And so because you have to take what you get and generate with the water that comes as it comes, it is variable, much like other renewable resources. It's going to be more predictable, let's say, than solar or wind. The weathermen are better about predicting river flows than they are maybe about forecasting sun and wind, particularly since river flows tend to be more hour by hour or day by day than minute by minute. So the opposite would be a storage type of plant. And I want to draw your attention in this photo to the water line, right? And you can see in this photo that there's this, bathtub ring around this upper reservoir. That's because it goes up and down. So you can see the high water mark. So a storage facility is allowed in its license a wider operational band for its upper reservoir. And it is usually cycled up and down usually daily and seasonally. And often will serve a dual purpose. So the seasonal variation would be more for flood control than for matching demand curves, which is what the daily cycling would be about. So you'd store water up at night, run your generators during the day, or as solar becomes more prevalent, run your generators in the morning and in the evening and shut them off at noontime. Pump storage is one of the, it's a rare bird in that there aren't a lot of them. They're very large, at least, conventionally. And they make up, some huge percentage of energy storage on the grid today. They're difficult to find a site for. Especially given modern environmental requirements. Often you find that these grew up alongside a nuclear plant. And again, that gets back to the word Steve used was flexibility of the resource. You can ramp and turn on and off a hydro plant very quickly. You cannot ramp or turn off a nuclear plant very quickly. So while the nuclear plant sits chugging along, satisfying base load for a region, the demand drops off at night, the pump storage facility will start pumping, providing a load for that plant and taking advantage of that cheap electricity to store energy in it from the lower reservoir to the upper reservoir, moving water from one to the other. During the day, when prices are higher, the pump storage facility will turn the pump around and become a turbine and generate electricity to supply the increased demand. So, as I mentioned, these are usually cycled daily. However, that is changing with the changing nature of the energy mix in our grid as solar generation becomes more prevalent and starts to put pressure on the grid and our generating resources. Pump storage is tending to be flexed harder. In other words, we're instead of cycling once a day, it might be cycling twice a day or more. So it's important to note that this much like a battery store, much like you'd think of a battery storage, this is a net energy consumer. This is not a 100% efficient process, right? Where let's say we're 90% efficient pumping, we're going to be maybe another 90% efficient generating. So that's not ideal, but it is. It does still have value, obviously, and there's market for it. Steve, you wanted to chime in?
Yeah, thank you. I was just going to point out, the question came to me a little while ago about trying to match those orange curves and gray curves. This would be another way you could do that is, when you're over generating, you pump and use that power to pump up and create that energy at night. Then when you need it, you would then reverse this. I just was going to point out this would be a really slick solution to that curve dilemma that question was asked earlier. That's all. So
yeah, it's definitely a consideration, and more broadly, perhaps energy storage more generally might be a consideration, right? battery electric storage systems are becoming quite common, almost commodity solutions. And more on that, 5, 10, 20 megawatt scale. Whereas for reference, a typical conventional pump storage facility is more in the order of, 500 megawatts to 1,000 megawatts. So we divided the projects into head, into high, medium, and low head. And this is as simple as it sounds, with hydraulic head being defined as the difference in elevation between your reservoir surface and your lower reservoir tail race surface. So a high head facility is probably not represented well by this cross section. Frankly, it would be much better represented by the very long penstock up the hill that we saw a few slides back. But the bottom line is we're going to choose different equipment for a high head versus medium head versus low head facility. We're talking, from I don't know where I'd draw the line. Maybe over 150 feet, maybe. It might be high head. And then medium head, this is maybe a better example of high head. They've called out 300 meters and 30 meters. And then low head. So all the fun is with low head. And I say all the fun because I mean all of the innovation seems to be around finding economical solutions for low head applications. There's not a whole lot of project sites available where we can develop new high and medium head hydropower projects. They've been developed or won't be developed. But there are plenty of existing dams across the country that have, let's say, between 10 and 20 feet of head that could be developed if there were, the right set of economic and environmental circumstances. So you see pictured here two examples of low head solutions. This S turbine is a pretty common solution where you've got a horizontal shaft machine and water flowing through a turbine that's maybe got adjustable blades. This would be a Kaplan turbine probably. But the challenge here is this is horizontal because it minimizes the civil costs of construction of the powerhouse. You don't have to dig as deep a hole to install this horizontal machine. On the right, you see an Archimedes screw. We'll touch on that again in a little bit. This photo is a mill, a historic mill in Maine that Kleinschmidt helped redevelop some 10 years ago or so. You can't see the equipment, obviously, but it's a picturesque site that obviously historical societies wanted to preserve, and folks that owned the mill wanted to redevelop it and make a dollar off it. So in the category of low head, usually you'll find lock and dams. So I threw this in here as kind of a subcategory of low head sites to give you an example and illustrate maybe the problem with developing hydro plants on existing sites and operating a hydro plant on an existing site with a lock. There's a lot going on here in this photo. and they're a busy place for commerce, marine traffic, and often they're relatively low head sites, and that makes selecting economical equipment a challenge. So there are, let's say, three main types of turbines. These three turbines could be categorized into two. We have reaction turbines and impulse turbines. There are variations on impulse turbines, but one main type that we consider for utility scale. So we've got Kaplan's over here, Francis in the middle, and then Pelton down here at the bottom right. So our chart here has head across the bottom and flow, discharge, cubic meters per second on the vertical. And so from this, we glean that a Pelton turbine is going to be better suited to situations, applications with higher head and maybe medium to low flow. A Francis turbine suits maybe most applications, middle head applications with more flow. And then if you've got a lower head application, this graph suggests 2 to 50 meters and lots of flow, then the Kaplan turbine would be more suitable, more efficient. So we'll take a closer look at each of these. Start with the Pelton turbine. So this is, again, an impulse turbine. And that means simply that we're spraying high pressure jets of water at these buckets. Picture a fire hose trying to turn this turbine. That's the idea here. And so it's the water, as soon as it hits those buckets, is deflected and returned to a tail race with a whole lot less energy than it had, with that energy being transferred into kinetic energy in the turbine. That water jet is usually, maybe it's one water jet, but more often it's a set around the perimeter of the turbine, and you can control the power into this turbine by turning jets on or off, and also by throttling the amount of flow through that jet with usually a needle valve. Francis turbine is a reaction turbine. This turbine is wet all the time, whereas the Pelton turbine, again, the water's splashing off it, it's operating at atmospheric pressure. Whereas with a reaction turbine, you have high pressure water on the top side, and you have low pressure, perhaps a vacuum here below the turbine. And so there's no air happening in here, and if there is, that's a bad thing. So the flow through a Francis turbine and through a Kaplan turbine is controlled primarily by what we call wicket gates. And I'm realizing now that this doesn't really call that out. We have guide vanes here. I guess that's the intent. But these wicket gates or guide vanes rotate and to a completely closed position where they all overlap each other, and they'll all rotate together to open up and allow flow to pass through the turbine. Which of course in this image is rotating a vertical shaft, whereas here again, this is a horizontal turbine, which is, I want to say that's typical for Pelton turbines, though I have seen vertical ones. Kleinschmidt and me in particular, we're well experienced with Francis and Kaplan turbines. I personally have not run into very many Pelton turbines, being on the East Coast particularly. Again, Pelton turbines being well suited to high head sites are going to be more on the West Coast. So here's our Kaplan turbine diagram. Once again, we have wicket gates around the perimeter of the turbine inlet. You can see that, water flows from outside to inside through the blades of the turbine to spin a vertical shaft. The important thing about a Kaplan is that the blades themselves also rotate. And so that ability of the blades to rotate to help control flow or change the reaction of the turbine improves efficiency over the range of flows that can go through the turbine. So that results in a much flatter efficiency curve close to that 0.9, whereas with a Francis turbine, you have a very steep efficiency curve where the turbine is most efficient at, let's say, 80% of its rated flow. So you're with a Kaplan turbine, you can get a wider range of flows through the turbine at reasonably good efficiencies, whereas one might tend to want to operate a Francis turbine as either on or off at best efficiency. There's less room for economical throttling or adjustment outside of, say, a range of maybe 60 to 100%. You wouldn't turn it down much beyond 60%. So yeah, innovative new turbine types. New is in quotes, you notice, because, precisely because of the Archimedes screw. It's making a comeback. I think I'm aware of one installation in Connecticut, and it's primarily attractive because it's considered quite fish friendly. It's a very slowly rotating screw, much like an auger that you'd use to put corn in a silo, for instance, but it's going the other way, right? Because it moves very slow, you're usually going to find it coupled with a gearbox. That's a whole mechanical engineering and maintenance discussion that we won't have, but the gearbox will then be coupled with a generator. And one of the other technological advancements or innovations that's enabling these kinds of technologies is the ability to connect this generation with variable frequency drives. Usually a variable frequency drive will be used to control the speed of a motor, right? So power through it in one way. You can also use variable speed drives, particular types, to vary the speed of a generator and take the power out the other way. At some, non-trivial expense addition. Cross-flow turbines is another type that you'll often see with low-head projects, and pictured down here on the right, you've got a submersible, we'll call it a bulb turbine, I guess, but this would be something like a Kaplan turbine, but its blades are going to be fixed for simplicity's sake. So this is a particular manufacturer's modular solution. So, as with anything, trying to make something modular and offer, a menu of solutions for a variety of applications is one way to cut costs, right? So if you can take 10 of something and install them because, that suits the application and that's the size that's available, that's probably going to be more effective, especially for low head sites, than developing, 2 turbines specifically for this application, this head and this flow. So when I'm talking about an application of a hydro solution or a turbine, we're talking about those 2 parameters, right? And so the application is mostly defined by the head and the flow that you have available in the river. So let's talk about the generator. That's the exciting part. No pun intended. You guys still awake?
Yes.
Yes.
Yes, sir.
Thank you. So we've been talking about the turbines and the water, and we've got obviously a shaft that connects that turbine to a generator. That's how we convert mechanical energy or mechanical power into electrical power and energy. So sometimes, as mentioned, that shaft will pass through a gearbox, particularly to solve economical problems in low head applications, because a turbine must turn slow and a cheap generator turns fast. A generator that turns slow is much more expensive than a generator that turns fast. So typically when we're talking about hydropower, we're talking about synchronous salient pole generators. Salient pole meaning the poles are individual and they stick out. We'll see that in a second. Synchronous meaning that the rotor or the center of the generator that is attached to the shaft is rotating synchronized with the electric grid, meaning there's no slip as there is with an induction motor, for instance. So synchronous salient pole motors, or synchronous, the typical hydro generator, synchronous generator has a field winding and a stator winding. The stator winding is the armature. The field is on the rotor. Worth noting, again, back to the kind of the low head, innovative side of things, permanent magnet generators are becoming more common, especially in that modular small hydro space, and particularly appealing if you have an application where variable speed makes a difference. Variable speed makes a difference, particularly when head changes greatly over the range of operation. So instead of a field winding with an electromagnet on that salient pole is a permanent magnet. Oh, there we go. There's my salient pole and the winding on that salient pole, and the pole head that keeps the winding from flying off. Here's a good 3D example of how these salient poles are wound. And you can, if you follow this closer than you probably can on your screen, then you'd see that these alternate polarity with the direction of the winding. So here we have an example of a horizontal generator. And this is obviously a very old generator, but you can see, and I chose this example because you can clearly see the salient poles in this photo. So this has many poles, which means it's a slow rotating machine. It is direct coupled to the turbine that's in this pressure case in the background of the photo. You'll also notice that this same shaft is connected to this itty bitty generator here. This is a DC generator. It's what we'd call the exciter for this machine. So this same shaft that generates the AC power generates DC power that is regulated in a plant this old, usually with a rheostat, and then put back onto the main field of the generator to create the rotating field with those electromagnets that are the poles. So, technology's changed a lot. Most modern hydro plants will not, I won't say most, no modern hydro plant that I know of would have a rotating DC exciter or rheostats. So today we'd have a power electronics solution that we'd call a static exciter. So we're manufacturing DC from AC with power electronics and regulating it with a digital controller, and then applying a regulated current to the field in order to control in the end voltage of the AC generator, or if not voltage, then reactive power or power factor. Usually those are your three options with a modern exciter. So let's talk a little bit about controls and automation. This is the only slide I've got on the topic, really, and I want to point out, the difference in, legacy plants, let's say, and a modern control room. And hard to say necessarily whether these are examples of a hydro plant. The old one, I'm going to say is a pretty good chance, because I've seen many hydro plants that have a control room that look pretty darn close to that 1940 something photograph, with instead of drawings stacked on the desk in the foreground, they'd have a computer and 3 monitors there, but they would often still have much of this legacy metering, controls and relaying board still there. So, you notice in the old photo, you've got all kinds of analog meters. And then in the foreground of that, you've got what I'd call bench boards with, control switches, discrete control switches for, switching breakers, raising and lowering excitation, raising and lowering governor set points, flow through the turbine, and that sort of thing. And then, the more modern photo you have, I guess what you'd expect, right? We have a large control, a large screen here for, multiple viewers in the control room to see things like, closed circuit TV, and, common screens that they're going to refer to throughout the day. And then their day-to-day tasks, their details, their actual operational interface is going to be through these, monitors on their desks. So the link here is obviously digital controllers, right? Programmable logic controllers or distributed control systems, and SCADA. So this example might not be a control room for a particular plant. This could be a regional control room controlling multiple plants. So yeah, that's I guess I want to reinforce that point. So you can have automated control at different levels in hydropower or anything. You can control things locally at the unit. You can control things centrally at the hydropower control room. If you've got 8 units, you can control them all from the one room, from the bench board, or from your desk and human machine interface PC. Or you can use SCADA, so that's SCADA, supervisory control and data acquisition, in a wider area to perform maybe more limited control functions at multiple plants. So you might be able to sit in a regional office and start and stop a generating unit, or change its power output set point from 80% to 60%, or you might be able to change its mode from a manual operator control to an area regulation control, where you're getting a set point from the utilities central command, if you will. I think that covers that. And then there's protection. So these are obviously very expensive assets that you owners want to protect and monitor. We want to protect them from themselves, as well as conditions outside of the plant. So this breaks down into 2 major categories. You've got electrical protection, which is kind of what I think of first when I hear the word protection all by itself. Electrical protection these days takes the form of usually little blue boxes, as pictured here on the right. It's a particular manufacturer that's got a lot of the hydro market, a lot of the utility market in general. But these little blue boxes are what we generally call a digital multifunction protective relay. The legacy approach to electrical protection is multiple individual relays, and you can take that relay for, you know, its legacy, meaning it's something electromagnetic that moves something mechanical like a contact, and that will in turn trip the generator's breaker and shut the governor and the exciter off, thus shutting down the unit. Today, you've got all of the necessary protective functions, you know, measuring current for overcurrent tripping, measuring voltage for over/under voltage, and frequency metering and tripping. You know, these are the parameters that we're measuring with these relays: voltage and current, usually of the three phases, and we're making decisions about whether or not those measured values are within acceptable limits. And you know, an engineer will set those limits in these protective relays, and when exceeded, the relays will trip the generator offline. The other category of protection is mechanical. And you know, the image to the left kind of illustrates the concept here, in that we're applying sensors of various types to the turbine generator unit to measure critical parameters like the temperature of the stator windings, because we don't want them to get, you know, exceedingly hot and you know, start damaging the insulation, the electrical insulation of the windings. We don't want, we want to measure temperatures of bearings, because we don't want to wipe the Babbitt material off the bearings. We don't want the oil in the bearing baths to get too hot. We're measuring vibration often, and you know, to make sure that the run out of the unit is, you know, within tolerance with it, to make sure that the you know, particular operating conditions of the unit aren't causing excessive vibration, or perhaps maybe even picking up cavitation. And what else? We can measure the air gap. That's the distance between the rotor and the stator. Obviously, if the rotor shifts because, you know, bearing tolerances have gotten bigger, or because the electromagnetics of the unit are off, if the rotor shifts, that's kind of a problem. So you can monitor for that. All those kinds of things, you know, it can measure temperature of cooling water, all those kinds of things. We can take all those instruments and aggregate that data via programmable logic controller or specialty hardware, and monitor those things and trend those things over time. We can use them for predictive maintenance, or we can use them for simple alarming to alert an operator that, you know, there's a high temperature or a high vibration, or you know, deviating air gap. And then the operator can decide what to do. Often we're not necessarily tripping the unit offline because of one of these parameters, though that is certainly possible. Usually it would be a more orderly shutdown if something's getting too hot. That's not a you know, explosive ground fault kind of problem. That's more of a, well, let's shut it down and let it cool problem. That is all I have prepared. I would be happy to entertain questions or go back to slides and discuss any questions you guys have.
Well, I learned a lot. I always learn a lot from these Hydro 101 sessions, so I appreciate you going into this detail. Does anybody have any questions for Lucas?
Yes, you said that it was not economical to use the entire flow of the river or the water source. I want to know why it wasn't economical. couple of reasons.
Well, so usually the maximum flow of the river is something that happens very infrequently, right? We hear terms like the 100-year flood. It wouldn't be impractical to build your powerhouse big enough and include as many turbines as you would need to take advantage of all of the flow that the 100-year flood has to offer. You'd have 99.9% of the time, one out of your 20 turbines sitting there doing absolutely nothing, or maybe 5 of them. And that gets to analysis of the hydraulics of the river system and flow duration curves, exceedance levels. But typically when you're sizing a hydropower plant for a river, you'd be looking to cover, I don't know, 2/3 exceedance. Somebody correct me. Steve, you got a better number? Somewhere around 2/3.
Yeah, this basically, yeah, you pegged it. I mean, effectively, the reason you don't build it to full capacity of the river, let's just say average flows, just taking averages, is because a significant amount of the time the river is below that. You don't have you have machines just sitting idle, so you're spending a lot of money on really expensive equipment that is never going to get used, or very seldom gets used, and that's where the economics come in. And just as he's saying, the rule of thumb kind of comes back to about 70% on your exceedance, on your duration curve. So in other words, based on averages and everything, you're designing your plants typically today for about 70% of the time. You're only about 30, well, it's 70% on the exceedance, but 30% of the time you have full flow for all your units, and all times less than that, there's less than full flow. And so again, it's just because you have idle equipment sitting there. It's really, these turbines and generators are super expensive to construct. And so you don't want an asset that you spent a lot of money not returning anything to you. So that's generally what the question comes down to. And you'll look, some of the really old stations defy that. In my old company, we had some generating stations that literally were sized at a very minimum flow. So they ran almost 100% of the time at full load, just because at the time they designed them, that's what the information they had. But newer plants, much newer plants, have a lot of time where there's just idle capacity.
And I've seen, many older plants, built in, the teens and 20s, where they clearly didn't have a really great understanding of the hydraulics, because they'd build a plant with, 6 units and have 2 or 3 extra, what I'd call a skeleton bay, or the infrastructure from a civil standpoint to install more units if they found it necessary. They'd find out later.
Okay, thank you.
Just one more point, but I think as you start getting some more information on this particular challenge, one of the things we contemplate is having this solution over several parts of the seasons, and you'll see that if that does happen, and Kenneth needs to kind of help weigh in on that, but you'll see the difference in the river flows, seasonally, and the variety, the range of river flows that you need to kind of design for. And so that's also part of the equation here. So it's a great question, one that comes up frequently, really. Why do you have these sitting here? But there is reasons for it. It's kind of an economic judgment on how all that works. Won't go into that now because it gets into the weeds a lot. But there's reasons, and basically it's just you don't want expensive equipment sitting idle year after year, never being used.
That makes sense.
Anybody else?
Yes, I got a question about
your
the
time.
concept of. Yes, yeah, I got a question about the concept of reserving the water when the resources are more than the demand, and then you reverse your turbines to work as pumps. Is there any, like, first of all, how often we use this practice in the actual life? And if yes, if we use it a lot, do we use a different equipment, or it's the same equipment, we just like control it differently? Thank you.
Yeah, fair question. So I'll go back to my pump storage slide. We can stare at that while I think about how to answer that. I think the first point I want to make is that yes, if you're planning on storing energy this way, it is special equipment. So you're either going to have a pump turbine that's specially designed to be able to pump in one direction and generate in the other. Or there are other arrangements where you could have a pump and a turbine on the same shaft and control flow with shut off valves and gates accordingly. And there are even conceptually these days there's variable speed technology that could vary the pumping much like a VFD would with a small pump, so that you could vary load, not just generation, because you can't throttle the pump in the same way that you can throttle it as a generator. Did that answer your question? So part one at least was how often we use it. So the cycling of pump storage facility is typically daily. As the graphic implies, usually we're pumping at night and generating during the day. It depends on how much physical water storage you've got. I mean, you could conceivably have multiple days worth of storage, but usually your project isn't going to be designed to run more than a couple of days in one direction or the other.
Can I add a little bit to that too? So the first, just like you said, the equipment is it's not conventional hydro equipment. It's special turbine pumps, pump turbines and so forth that do this. And you got to understand, he was talking about the generators a while ago. And when you're generating, the shaft moves in one direction, and when you're pumping, you got to move the shaft in another direction. So there's phase reversals, or you can use the variable frequency type technologies to do things. So it's a little more complex without question. The other thing I just wanted to point out, is batteries came up in the discussion, and that's great. But just as he was alluding to here, pump storage typically has much longer duration in terms of generation back than batteries. Batteries are, batteries are great for a day, and they're usually, rule of thumb, 4 hours worth of storage, whereas pump storage can give you multiple hours and sometimes even days of storage. And so they have a different kind of a value proposition, if you will. The pump storage is much larger, much bigger, much more expensive, but it has because of the duration of the storage, it's actually quite beneficial in many ways. And it's one of the reasons why there's a lot of pump storage being considered throughout the nation to try to address some of the shortages that are being projected now because of the movements to wind and solar, which is much more intermittent and not always there. So you need sometimes some long duration storage. It's a complicated challenge, and the technology to do it is pretty well understood, but there's always innovation moving on these things.
So we can also call it a hydro battery. The hydro battery used like on shores or where the water, like the seawater.
So
if you have more resources with the wind turbines, yeah, great.
I was going to say there's actually a company that patented that term hydro battery for a small. They were looking to build modular pump storage systems, much smaller than the, I think around, like, if I recall, I think it was like about an 80 megawatt solution. It was much, much smaller, but that's what they were calling them, as hydro batteries. And they, I think, patented the term and stuff. And to this point, none have been developed, but yeah, you could call it a hydro battery.
That makes sense. Thank you.
Any other questions? If not, I will relinquish control. And turn it back to you, Bree.
Thanks, Lucas. And if you all think of something, please don't hesitate to chime in or raise your hand, because I know sometimes it just, as you're thinking about things, you might come up with a question after we've talked about some other things. So just want to give you that opportunity. Hopefully you learned a lot today, and maybe some of you, this is review, I'm not sure, but hopefully it was educational. I know I always learn something new every time I listen to these. So really appreciate Lucas giving us his time today to teach us about hydro and all the components that go into it. So real quick, I was just going to kind of cover some housekeeping things. Like I mentioned earlier, I'm going to be sending you all a plethora of information so that you have it to refer back to in your email. That will include the recording from today. I was going to ask Lucas if he could share his slides so that maybe we could share those as well with
I'm sure I
students.
can do that.
Okay, perfect. And then also your team assignments, the logistics, the hotel information, and the problem set will come maybe later and early next week is what I'm trying to say. So you'll be getting all of that information, which will be helpful to you, and will get you all reserved in your hotel room. So they'll be expecting you between that 4 to 7 time frame on May 14th. It's not a hard time. I just kind of put that so that mostly for me to know that you made it okay, because we will start first thing on Tuesday morning on the 16th. We're going to have breakfast there at the hotel between 7 and 8 in the morning. So I think it's best if we can get there on Monday evening at a reasonable hour so that you can get some good rest, because we have a full day on Tuesday. We'll get to tour Bartlett's Ferry. We'll hear from many speakers, some from our sponsoring organizations that are going to teach you guys some more information, not just about the actual challenge, but also give you some insight into careers in hydropower, whether they be federal or with the private utilities. There's just a lot of opportunity in hydro, and we're going to learn more about water management and things of that nature. So we're going to teach you a lot in a few days. So think of it like hydro camp. It's super fun. It's meant to be fun. So I hope we didn't scare you today with a lot of information. But I think if you put into it what you want to get out of it, then you really will leave with a tremendous opportunity. So if you have any questions, I will definitely take them. Otherwise, plan on getting some information from me and get a few minutes back to your day. Any last questions? Okay. Thank you very much for making the time today, everybody. And I look forward to meeting you all in person. Super excited about it. And it's just a week and a half away. So
Thank you so much for the talk. Have a great day.
Wonderful. Nice to
Bye,
see you.
everybody.
Thanks.
Bye.
See you.
Good luck.
That's right. Good luck.
Thank you.